Hi everyone, I'm Arpita Vats. I'm currently doing my PhD from Santa Clara University with mainly focusing my research on computer vision and deep learning. Today I will be presenting our paper on key point-based driver activity recognition. In this paper, we have addressed the problem of distracted driver while driving. Driver activity recognition is an important task in order to find out if the driver is distracted or not. This was a part of AICT challenge where we were given a video on 5 different drivers using 3 different cameras, dashboard, rear, and right, with 18 different activities as a type of distraction. So we came up with the approach of the key point-based activity recognition framework named KENDER. The main idea of our method is that driver activity can be determined from the movement of key points on their body. We use a pre-trained pose estimation model to identify the key points and derive feature from this key point. The feature we design includes angle between key points, distance between the key points, and position information. We devise a merge algorithm to identify the activity segments by merging sequence of same activity of sufficient length after first removing the outliers. This is the architecture of our proposed method, where you can see in training dataset we have a training dataset from 3 different cameras, dashboard, rear, and right side, which is then passed into for feature extraction, which includes skeletal feature extraction as well as a facial feature extraction, which is then created into a dataset and then passed into a classification model, which is XGBoost classifier in our case, and then a merge algorithm is applied on top of it to finally give that output and define the type of distraction for a particular frame. Our framework uses a feature extracted from the frames in training set videos, along with their associated labels, which were provided by the organizer to train a classification model that is able to predict driver's activity in the given frame. Our model is able to predict the frame-wise training set activities fairly well, as some outliers do appear from time to time. Having been told that the test set follows a similar pattern as the training set, we devise a merge algorithm to identify the activity segment by merging the sequence of the same activity of sufficient length after first removing the outliers. So a shorter list of class prediction is given as an input, which is then combined with the individual per frame prediction of the activity classification model into segments, and then looks for the class that having higher percentage of prediction than expected, and returns the result as a maximal consecutive class segment of the length. We executed a series of experiments over all combinations of the following parameters. We extracted features from the dashboard, rear view, and side view, taking keyframes every 3, 5, and 10 frames of each video, and extracted features both with and without facial features. We split the training data set into a training set and a validation set using 80:20 ratio, split and train a large number of XGBoost model, optimizing for the best validation F1 score. F1 score with a facial feature was 0.95, whereas F1 score without facial feature is 0.9662. We were also ranked 11th position in the AICT challenge on the public leaderboard. We also used a merge algorithm for segment activity classification. Our framework relies on pre-trained human pose estimation model to detect humans in the video and their associated poses. While any such model may be used, we have used Kappa model that gives us an image extracted from the video. The model identifies the point of those pose of any human in the images. We design our method to extract both static feature based on the current keyframe at time t and motion feature based on difference between the current and the past frame at the time t minus k. This strategy not only allows faster processing but also enhances our motion feature as the driver's movement will be more pronounced between the keyframes. The meta parameter k must be carefully chosen in order to ensure the capture motion features are meaningful for the frame activity classification problem. In this work, we presented a framework for driver activity prediction that uses off-the-shelf pre-trained human pose estimation and facial feature detection model to predict the time sequence in which the driver is performing one of the set of predefined action. Our model first extracts a series of both static and movement-based features from the keyframe in the videos and then uses a classification model to identify the potential action being performed in each frame. And finally, it uses the merge algorithm to merge the sequence of action prediction into a robust action segments. Some of the future work that could be done is object detection using YOLO v5, improving the driver identification problem, improving the merge algorithm, especially it should not rely on the challenge activity statistics. Thank you.